Hi everyone, in this video I would like to discuss today's biweekly contest 185. So let's jump to the first problem of this contest. So first problem says that you are given two integers m and n representing the number of rows and number of columns of the grid. Construct any m cross n grid consisting only of the characters dot and hash, where dot represents a free cell, hash represents an obstacle cell. Now let's define a valid path. A valid path is a sequence of free cells such that it starts from the top left corner of the grid and it ends at the bottom right corner of the grid, right? And there are only two moves allowed here, that is right and down. At the end you need to return a valid grid such that in that grid there is exactly one valid path from top left cell to the bottom right cell of the grid, right? So if we see the sample test case 1, we see that if m equals to 2 and n equals to 3, we can have a grid having this only this as the valid path, right? And for the sample test case 2 also, we see that this is the only valid path. So this is a pretty easy implementation problem. What we can do is we can just mark the topmost row all dots and just mark the top rightmost column all dots. Then you will have only one valid path, that is topmost row then rightmost column, right? So let's implement it. Let's create a vector of string for storing the grid, and first let's push the first row having all dots. Now add the remaining rows. Let's create the current string representing the current row. So for the first n minus 1 columns of the row, add hash, and for the last column, add dot. Add this row to the answer grid. Return the answer grid. Okay, so let's move to the next problem. Here is our next problem: minimum lights to illuminate the road. The problem says that you are given an integer array nums, integer array lights of length n representing positions from 0 to n minus 1 on a road. For each position I, there is a light, let's say lights of I equals to v, where v is greater than 0. It means that if v is greater than 0, then it means that there is a working bulb at position I. It illuminates every position from I minus v to I plus v, right? Taking into taking into consideration the indices, right? From 0 to n minus 1 it should be there. So it is taking maximum of 0 comma I minus v to minimum of n minus 1 comma I plus v, right? So basically if there is any working bulb, it will illuminate from position I minus v to I plus v. Let's say if there is a lights of I equals to 0, it means that there is no working bulb at position I. Now say that a position is visible if it is illuminated by at least one working bulb, right? So you may install additional bulbs at any positions. Each additional bulb installed at position j illuminates the positions from j minus 1 to j plus 1 inclusive, right? At the end you need to return the minimum number of additional bulbs required to make every position on the road visible. If you take an example of the first sample test case, it means that there are no working bulbs here. So what we can do is we can install the additional bulb at position 1, then it will illuminate the first three positions, right? And there will be one position left, so we will have to install one additional bulb here, right? So in total we will need two additional bulbs. If you take an example of this test case, then it says that there is a working bulb at this position. Now let's visualize it. So this is the lights array we are given currently, and at this position we have this working bulb, right? At this position. So this is I equals to 3, right? At I equals to 3 we have this working bulb. And now the range it will illuminate is, the range of indices this bulb will illuminate is from I minus 2 up to I plus 2, right? And this will illuminate I minus 2 is 3 minus 2, that is 1, and 3 plus 2, that is 5. But as the last index is 4, right? This is fourth index, so we will take minimum of 5 comma 4. So this is the range this bulb will illuminate, that is from first to fourth, and this will remain unilluminated. So we will have to install one additional bulb here, right? So answer for this test case will be 1. Now see how we can solve it for a general lights array, right? So first of all, what we will do is we will find which all positions are already illuminated by the existing working bulbs, right? And let's say there are some remaining positions which are unilluminated. So then what we will do is we will just optimally add one each of the additional bulbs such that it can illuminate maximum number of unilluminated positions, right? So let's implement it. So first what we need to do is we need to find the positions which are already illuminated, right? So let's take a vector, boolean vector, and what it will do is it will, so visited of I, it will store that visited of I equals equals to true if ith position is already illuminated by the existing working bulbs. Otherwise it equals to false, right? So let's see how we can find this visited array. So let's fill this visited array. So first of all, let's take an index and iterate this lights array from end to the starting position. If this is a working bulb, then what we'll do is we will mark all the positions illuminated by this bulb as true, right? So let's do this thing. Assign index of index equals to minimum of index comma I plus lights of I, right? And then mark all the positions which are illuminated by this bulb. I minus. The range this bulb will illuminate is from I minus lights of I up to I plus lights of I. Mark this position as true and also decrement I by 1. So this is we iterated from right to left, also iterate from left to right. Iterate from left to right. If this position is if this position is having a bulb whose value is greater than 0, it is a working bulb. Then let's take index equals to maximum of index comma I minus lights of I. Illuminate all the positions towards right, towards right, which are illuminated by this bulb. Okay, now we have all the positions which are already illuminated by all of the existing working bulbs. Now just fill the additional bulbs. If this position is already illuminated, right, we will just increment I by 1 and we do not need to add any additional bulb here. If this is not an illuminated position, then what we will do is we will install an additional bulb at position I plus 1, right? Add an additional bulb at position I plus 1, then it will illuminate position I minus 1, I and I plus 1. Assign I equals to I plus 3, right? Because it will illuminate positions I plus 1 and I plus 2, right? So at the end, return the answer variable. Also, why we are doing I plus 3 here? Because positions I plus 1 and I plus 2 are illuminated by an additional bulb at position I plus 1, right? We have installed an additional bulb at this position I plus 1. So let's submit this code. We are having runtime error. Are we missing something? Oh, we should do index of plus plus. Also do this thing, index minus minus here. Okay, great. So let's move to the third problem. Here is our third problem. The third problem says that you are given an integer n representing the number of tasks in a project, numbered from 0 to n minus 1. These tasks are connected as a tree rooted at task 0. This is represented by a 2D integer array edges of length n minus 1, where edges of I represents an edge from UI to VI, indicates that the task UI is the parent of task VI. You are given an array base time of length n, where base time of I represents the time to complete task I. The finish time of each task is calculated as follows. For each of the leaf tasks in the tree, the finish time is its base time. For all the non-leaf tasks, let earliest be the minimum finish time among its children, and latest be the maximum finish time among its children. Then its own duration, lets its own duration be latest minus earliest plus base time. Then the finish time of task I is latest plus its own duration. Okay. At the end, you need to return the finish time of root task 0, right? If you see the constraints, it is 10 to the power 5. So they are expecting us to solve this problem in linear time. So this is also a pretty easy problem. So what we need to do is we just need to find the calculate the finish time of each of the task, right? So what we'll do is we will start from the leaf nodes, right? For the leaf nodes, the finish time is its base time, right? And we will just move one step up, right, from leaf to their parent. Now for the parent of the leaves, we already know the finish time of all of the leaves. According to this rule, we will calculate the finish time of this parent, right? Then again we will move to its parent's parent, right? So this is how we will, from bottom to up, this is how we will calculate the finish time of each of the node. Ultimately we will calculate the finish time of the root node. So this is just an implementation problem. Let's first create an adjacency list here. So we have added all the edges to our adjacency list. Now create a DFS function. It will return a long integer, and it will take an integer as input. Let's call it DFS. S is the, let's call S as the current node which we are going to traverse, and also take a variable, this is the earliest, right? So first of all, let's check if this is a leaf node or not. If adjacency of S is empty, it means that it is a leaf node. Then we will just return the base time. Otherwise, define two variables, earliest, right? Let's define earliest. What is earliest? Earliest is the minimum finish time among all of its children, right? So initially let's define it as infinity, and let's also define another variable, that is latest. Latest is the maximum finish time among its children. So let's initialize it with 0. Also define a infinity variable here. Okay, now iterate over its child of s. Let's say the finish time of this child is ft, finish time, and now e is the minimum among all its children, and latest is the maximum among all its children. at the end our finish time of this particular node S is latest, that is L, plus on duration. What is on duration? On duration is latest minus earliest plus base time of S, right? At the end we just need to find the finish time of 0th node. Okay, so let's make it long. No matching function for call to minimum. Okay, let's also make it long because the finish time can exceed the integer range. Great. So let's move to the next problem, that is the last problem of this contest. This problem is count good integers in a range. So you are given three integers LR and K. A number is considered good if the absolute difference between every pair of adjacent digits is at most K. Return the number of good integers in the range L to R inclusive. The absolute difference between values x and y is defined as absolute of x minus y. Great. So from the problem itself, if the constraints are large, that is constraints are obviously large enough, 10 to the power 15. So this problem is expecting us to solve it in order of a log of r minus l, right? We cannot solve it in linear time. So logarithmic time we need to solve this problem. And this is a pretty standard problem if you see from the point of view of digits dp, right? So that's what we are going to implement here, digits dp, right? So the problem is obvious, we do not need to solve any of the sample test cases, right? It is pretty understandable. So let's implement the digits dp here. So for digits dp, first of all, what you need to have is you need to have the digits. Okay, so first of all, let me create a base for this dp, digit dp, if anyone doesn't know, right? So let's define this problem in a different way, right? So let's say you are given an integer n. Okay, you are given an integer n. Now you need to find the number of good integers between 0 to n inclusive, right? This problem we can solve with digit dp, right? Let's first solve this problem, right? Create a function who calculates the number of good integers between 0 to n. Okay, so first of all, let's create a vector of digits which will store the digits in the integer n. Also, let's take int k, that is the condition for the good integer, that is the adjacent digits difference must be at most k. Okay, and and the end, let's take a dp of size 16, 11 and 2. Okay, first of all, forget this forget this thing. Let's create a function. Let's call this the good integers. Okay, good integers, this function will take input as I, last, and boolean variable. It says that if this particular integer is already small or not, right? Okay. How should I explain this DZTP? First of all, let me implement it, right? I will explain it while implementing. Okay, so let's define this function. What does this function return? Good integers of I comma last comma small. Okay, one another thing, if someone is interested, before doing this problem, it will be very helpful if you learn more about what actually is a digit DP, right? So if you can read out some of the blogs on, you may easily find some of the blogs for digit DP, maybe code forces, right? So you can easily look some of the blogs which so this is their pretty good blog on what actually is DZDP, and it states the problem itself and how to solve this problem using DZDP, right? So I will first recommend to read out some blogs, and if then after, let's say, you understand what actually is DZDP and what kind of problems DZDP can solve, then it will be pretty easy for you, right, to follow along this solution of this problem. So first of all, let's define what. So first of all, we are going to solve this problem. That is, then we are going to find the number of good integers between 0 to n, right? So for this, let's define this good integers function. So what it does is, good integers of I last small. It says that we we know it says that actually it says that your last means I minus, it says that I minus I minus one digit, right, from I minus one digit is last, and if small is true, right, if small is true, then it says that you have iterated from the maximum uh, digit to the smaller digit. So let's say, let me take an example of an integer. Let's say the int n value of n is this, right? So what you will do is, here is, you will start iterating from this 1, then 2, 4, 5, 6, 6, 7, 6, 6, 7, right? So you will iterate from left to right for for the integer n, and I represents the index, right, from index of the digit, right? So let's say this is the 0th index where 1 is there, this is the first index, this is the second index, this is the third index, right? So this is the thing, and this integer is stored in this digits array, right, or we can say digits vector. So we have stored n in this digits vector, and now we are iterating over the digits from left to right, right? So what does this function do? Good integers. What it says is, you are currently at ith digit, okay, and the last digit of the number, last digit of the integer you are going to evaluate is last, okay, and while coming from 0 to I, you have already taken a smaller digit in any of the index from 0 to I minus 1, right? If you have already taken a smaller digit in 0 to I minus 1, it makes your current number already small than n, right? And how will it help is, okay, so if this number is already smaller than n, then we can take any digit afterwards, right? Afterwards of I and up to the last digit, right? So let's implement this function. If you are not getting it, I'm sorry. This is a little hard to explain without knowing DZDP. So earlier I also said that it will be very helpful if you first read out about DZDP, then come to this problem. Then it will be very understandable for you, and you will easily understand everything here. So let's implement this function good integers. So if I is already at the last digit, right? If I equals to digits dot size, it means that we have covered all of the digits of n, right? Then just return 1, that this is a, as we have covered all of the digits of n, then say that we have already evaluated that this is a good integer, right? Otherwise otherwise what we will do is we will also, let's take this long, right? Also take this long, okay. Now let's take a result variable, right? It will store the result of the number of integers we can form for upcoming digits, right? So let's say if this number is already small, right? It means that we have taken at least one smaller number from the index 0 to I minus 1, right? If it is already small, then we can take any of the digit d equals to 0 to d less than 10. If uh, also check one thing, this digit minus last digit, its absolute value must be less than or equals to k. Then you, what you will do is you will just add result plus equals to good integers of I plus 1. Now your last digit is d and it is already small, right? For the else case, now see that this number is small is false here. It means that this number is uh, equal to n, right? Up to the point I minus 1, right? Up to the index I minus 1. Now what you can do is you can only take digits from 0 to digits of I, right? Let's say if you take any digit, let's say digits of I plus 1 or digits of I plus 2, then what you will see is this number is greater than n, which you don't want because you want good integers in the range 0 to n. So in this case, first let's take digits smaller than digits of I, right? And do the same thing. If the absolute difference is less than equals to k, add it. Also here, as we have taken a smaller digit than digits of I, it will make the it will make your current integer as small, right? So you will pass true here. Now you will check if absolute value of d minus digits of I is less than or equals to k. It means that you can take this current value of the digits as digits of I. Sorry, it last minus digits of I, right? If the absolute value difference between last digit and the current digit, that is we are going to take digits of I. If their difference is less than or equals to k, then we can take digits of I at the position ith, right? So let's add into the add here this value. Good integers of I plus 1. Here we have taken digits of I, okay, and this is false because this number is not small. We are only taking a number equal to the digits of I, and all earlier digits were equal because this is already false here. False means we have not taken any smaller number than any of the previous digits. Okay, once this is done, just return your result value. Also, we need to uh, memorize this recursive function. So let's memorize it, right? So let's check it here. If dp of I comma last comma small, if this is not equals to -1, then just return it, right? At the end also just return it. Also, there is one another thing we need to notice is if the last integer if we haven't picked any of the previous digits, that means that all of the digits before I are 0, that it means that we haven't picked any of the uh, digit greater than 0, right? It means that our number is the most significant digit of our number haven't started yet, right? It means, so how we can track this, right? So why I am worried about this thing, that we haven't picked any of the significant digit up till I. I am worried because if we haven't picked any of the digit greater than 0 from 0 to I minus 1, then we will not apply this condition, right? So for tracking this, what we can do is we can use last equals to -1. Let's introduce a more digit, that is -1. -1 means that we haven't picked any of the digit before I. Okay, so let's here we will take if dp of I last plus 1 not equals to -1, then we return this, and here return this. Okay, also add a more condition here, that if last equals to -1 or, right? Why we are adding this? Because we don't want to apply this condition if we haven't picked any of the digit before index I. Now also pass the value of last right here. So see that if you see that if if last if last is -1 and d is 0, then we will pass -1 here, otherwise we will pass d. Okay, similar thing here. And for this we will keep it as it is, because if we are adding a particular digit here, then we are sure that we are passing a non-zero, we are already having a non-zero digit before this. Okay, so now let's implement the main function here. This of k, let's assign the value of k here, and let's clear the digits vector. Okay, also set all the states of this dp -1. Okay, now get the digits of the integer r. Once we have the digits right in the correct order, now we have the digits of r, right? Let's define answer function. So first calculate the number of good integers between 0 to r. How you can calculate this? You can simply use this function. This is just the initialization, right, to prepare this function call. Okay, so this is where we are finding the number of good integers between 0 to r, right? Start from position 0, last element is -1. -1 says that we haven't picked any most significant digit, non-zero most significant digit, right? And it is not small. Now what we'll do is we will remove the good integers from 0 to l minus 1. Again do the same thing here. Prepare the function, right? So clear these digits and initialize the all states of this dp as -1. And as we are calculating from 0 to l minus 1, let's insert all of the digits of l minus 1 into digits vector. So while l is greater than 0, add its digits. Okay, once this is done, we will subtract all of the good integers between 0 to l minus 1, and at the end return our answer. Let's run it. Memset. For first one output is 3, for second one output is 2. Okay, let's submit it. Great. So this was all for this video. I hope you got the solutions. Let's meet in the next video. Thank you.